Section 13.1, Graphs, Paths, and Circuits. A graph is a finite set of points called vertices connected by line segments called edges. A loop is an edge that connects a vertex to itself. Example, using the definitions of vertex and bridge, represent the Königsberg bridge problem with a graph. Königsberg was situated on both banks and two islands of the Prigel River. From the figure, we see that the sections of the town were connected with a series of 7 bridges. There's a picture of the town, the 2 islands, and the 7 bridges. We'll come back to this in the next section. The townspeople wondered if one could walk through town and cross all 7 bridges without crossing any of the bridges twice. Label each piece of land with a letter and draw edges to represent the bridges. So we're going to take the picture of the city with the islands and create a graph to represent it. And here's what it would look like. So we notice we have 2 banks of the river, and they're labeled as A and D. And we have the 2 islands, B and C, and we have a series of bridges. And remember, the edges don't have to be straight lines, but those are the lines that connect the vertices. The figure shows the floor plan of the Phenomenal Fitness Gym. Use a graph to represent the floor plan. When you're going to create a graph of a particular application, you want to look and see what kind of relationships you see between the different parts of the picture. And if we notice in this picture, to get to the outside from the physical fitness rooms, we can go 3 ways. We can go in each end of the health and weight room and also from locker room A, but not from any of the other rooms. We notice that the locker rooms don't connect directly to the health and weight room, but the different training rooms do. And so here's what it looks like when we represent it graphically. And notice again, we can get from the health and weight room outside. We can also go outside from locker room A. We can go from Ray's training room to either the health and weight room or to locker room A. Same thing for Sierra. We can go from her training room to locker room A or to the health and weight room. And likewise, a similar relationship on the bottom part of the gym. The degree of a vertex is the number of edges that connect to the vertex. A vertex with an even number of edges connected to it is an even vertex, and a vertex with an odd number of edges is an odd vertex. In this figure, vertices A and D are even. A has 2 edges connecting to it, and D actually has 4. A loop counts twice because there's an edge connecting this way and an edge connecting that way. And B and C are odd. Which of the following graphs has 4 even vertices and no odd vertices? So if we go through them one by one and we look at choice A, we see that A and D are even and B and C are odd. So that's not the correct answer. We look at B, it looks like all 4 of those are even. And we look at C, we see that all of those vertices are odd. So the correct answer here is B. A path is a sequence of adjacent vertices and edges connecting them. Here's an example of a path. We start at vertex C, we travel to D, then up to A, and then to B. A path does not need to include every edge and every vertex of a graph. In addition, a path could include the same vertices and same edges several times. So for example, on the next graph here, we see we could just keep going around and around, A, B, C, D, A, B, C, D. Those would be a path that just keeps going and going. In the graph below, AB is A, B, C, D, E, a path. Explain why or why not. So let's trace it out and see. A, B, C, but there is no edge between C and D, so this can't be a path. A circuit is a path that begins and ends at the same vertex. So if we take this here, I'm not sure where we're starting. Let's say we started at A, we went to A, to C, to B, to D, and back to A. A graph is connected if for any 2 vertices in the graph, there's a path that connects them. So if I pick any 2 vertices in this graph here, there is a way to get from one vertex to the other through 1 or more edges. A graph that is not connected is called disconnected. Here's a disconnected graph, here's another disconnected graph, and a third one. Let me just go back for a second. This may look like it's connected, but where these 2 edges cross over here, there is no vertex. So there is no way to get from A to C or A to B, etc. Determine if each graph is connected or disconnected. So let's take a look at this graph here. We see this as disconnected because we see that this part of the graph here has no connection to the square part of the graph in the background. This graph here looks like the same graph. Actually, all that happened here was that vertex C actually was pulled up and put into vertex B here, and this graph is connected. A bridge is an edge that, if removed from a connected graph, would create a disconnected graph. And we go back to, these were the disconnected graphs that we had earlier. If we put a bridge between A and B, we actually make a connected graph. Same thing here. This edge here between C and E is a bridge. If we remove it, we create a disconnected graph. And this was the earlier disconnected graph we have. Actually, once we put a connection here, for instance, between an edge between A and B, we have a connected graph, and now we actually, all the edges here are all bridges. If we take any of those edges out, we create a disconnected graph. In this connected graph, identify any bridges. So if we look at it, we notice the only possibility here is BC. Edge BC is a bridge. Now in section 13.2, we're going to talk about some very special Euler paths and Euler circuits. An Euler path is a path that passes through each edge of a graph exactly once. An Euler circuit is a circuit that passes through each edge of the graph exactly one time. Remember, the difference between a path and a circuit is the circuit starts and stops at the same vertex. So here's a graph, and here's a Euler path, and it starts at D, goes D, E, B, C, A, B, D, C, and E. It's a path because it does not start and stop at the same vertex. There's a slightly different graph, and here's a circuit on this one where it's beginning and ending at vertex D. And you can trace through that and verify that actually is a circuit. It hits every edge one time. Euler's theorem tells us for a connected graph, the following statements are true. A graph with no odd vertices, that means all the vertices are even, has at least one Euler path, which is also an Euler circuit, and it can start and end at any vertex. A graph with exactly two odd vertices has at least one Euler path, but no Euler circuits. Each Euler path will begin at one of the odd vertices and end at the other one. A graph with more than two odd vertices has neither an Euler path nor an Euler circuit. So if we return to the Königsberg bridge problem, we still wonder, can we take a walk through that town and cross each bridge exactly once? So remember our picture, the graph that we made, and we want to look at that graph and say, let's look at the vertices. We've got four odd vertices. A, B, C, and D are all odd. And what did Euler's theorem tell us? According to item 3, if there's more than two odd vertices, there's no Euler path nor Euler circuit. So there's no way to walk through that town and cross each bridge exactly one time. Fleury's algorithm is helpful to finding the Euler path or Euler circuit. First, you use Euler's theorem to determine whether or not that Euler path or circuit exists. If it does, if it has no odd vertices, then you can choose any vertex to start. If it has exactly two odd vertices, and therefore there's only one Euler path, choose one of the odd vertices as the starting point. Begin to trace edges as you move through the graph, number the edges as you trace them. Since you can't trace any edges twice in an Euler path and Euler circuit, once an edge is traced, consider it invisible. When faced with a choice of edges to trace, choose an edge that is not a bridge. Continue until every edge of the entire graph has been traced one time. On the next slide is a representation of the Country Oaks subdivision of homes. The neighborhood association is planning to organize a Crime Stopper group in which residents will take turns walking through the neighborhood with cell phones to report suspicious activity to the police. We actually saw this graph earlier. We said this was a connected graph. Can the residents of Country Oaks start at one intersection, which is a vertex, and walk each street block, which is an edge, in the neighborhood exactly once and return to the intersection where they started, and if so, determine a circuit that could be followed to accomplish their walk? So the first question is, does an Euler circuit exist? There are no odd vertices in this graph. They're all even. And so by item 1, there's at least one Euler circuit, and it tells us we can start anywhere, and we're going to decide to start at A. So we're going to walk along from A to B, and then we'll go all the way around the exterior of the neighborhood, and we'll come back to vertex E. And then from there, we can go to B to F, and there we have a choice. We'll probably just go ahead and go up to probably then C to G, and then finally down through J to F to I to E, and then back up to A. And so there is our Euler circuit. Use the following graph to determine an Euler path that begins with vertex A. So an Euler path, remember, passes through each edge exactly once. And if we try this one, we can go from A to B, so A to B to D to E to C to A to D to C. Is it possible that an Euler path exists with vertex B in this particular diagram? By Euler's theorem, vertices B, D, and E are even, the other two are odd. So if we're going to work with this graph, Euler's theorem tells us a graph with two odd vertices has at least one Euler path. It has to start in an odd vertice, and that's not B. B is an even vertice. So no Euler path exists that starts with vertex B. Use the following graph to determine an Euler circuit that begins and ends with vertex A. So all the vertices are even, no odd. The graph has at least one Euler path. It's also an Euler circuit. We can start and stop at any vertex. So here's an example. We could go A, B, C, D, E, F, back up to B, then to D, to F, and back to A. Use Euler's theorem to determine if an Euler path exists. If yes, what is the path? So how many odd vertices? There's two, A and B. And so then we know we have to start with one of those. And let's say we start with A. So we can go A, B, E, D, C, A, D, B. Determine an Euler path through the map that begins at N. These look like they're states, actually, don't they? And so let's take a look. And we're looking at a path here. A path doesn't have to start and stop. It's not a circuit at the same vertex. So let's start with the first one. Let's try this one. So we're going to go NU, DX, RL, NU. We've missed one here. We've missed something right in here, haven't we? Because there is a connection between N and R. Let's try B. NL, RX, DU. Again, we've missed a connection between U and N. Let's try C. NU, DX, RL, NRU, and that looks like the correct answer. Let's just double check the last one, which says NRUDX, and X can't go from, you can't go from X to L, so the correct answer has to be C.